So this is the contents of this presentation. Network function, Hurwitz polynomial, and positive real function, properties of LC immittance functions, and then synthesis of LC driving point immittance and synthesis of LC circuits, examples of synthesis, and then applications. So this is the brief contents. And network functions. Network synthesis is about the synthesis of various networks which consist of both active, means energy sources, etc., and passive elements, means resistor, inductor, capacitor, etc. What is a network function? Network functions are the ratio of output phasor to input phasor when phasors exist in frequency domain. So how it will look like? So I will show you. This is how a network function will look like. It is a function in S domain or frequency domain. So there are two polynomials, in the numerator one polynomial and the denominator another polynomial. So the three main necessary conditions for the stability of this network are given below. The degree of the numerator Fs should not exceed the denominator by more than unity. So there can be one difference of 1, m minus n, but it should be less than or equal to 1. Either there should be no difference or the difference can be 1. And Fs should not have multiple poles on j omega axis or the y-axis of the pole zero plot. Pole zero plot, you may be knowing, this is real part on x-axis, imaginary part on y-axis. The poles and zeros are plotted on this. So in this case, you should not have multiple poles, double pole, etc. on the j omega axis. And then Fs should not have poles on the right half of the S-plane. So in this portion also, in the right half of the S-plane also, there should not be any poles. Otherwise, what will happen? Otherwise, the function will have, for a bounded input, it will have unbounded output. So that is what is known as instability. So the function will be unstable if these conditions are not met. Then Hurwitz polynomial. So if we have a stable network function, then the denominator Fs is called Hurwitz polynomial. Or in other words, if the denominator is Hurwitz polynomial, that is a mandatory condition for Fs to be stable. So Qs is a Hurwitz polynomial if Fs is a stable function. Then properties of Hurwitz polynomials. For all real values of S, real values S of the function, P of S should be real, the numerator portion. The real part of every root should be either 0 or negative. Means, but this will ensure the no poles in the right hand side of the S-plane. And let us consider the coefficients of denominator b, bn minus 1, bn minus 2, b naught, etc. Here it should be noted that these must be positive, bn etc. should be positive, and among these bn and bn minus 1, they should not be equal to 0 simultaneously. Otherwise, it is not a Hurwitz polynomial. Then the continued fraction expansion of even by odd or odd by even part of Hurwitz polynomial should give all positive quotient terms. This is also another condition. So in case of purely even or purely odd polynomial, we must do continued fraction expansion with the derivative of the this function, polynomial function. And the same condition, same rules will apply for that also. So from the above discussion, what it turns out is, if all the coefficients of a quadratic polynomial are real, and positive, then that quadratic polynomial is always a Hurwitz polynomial. And positive real function. Any function which is of the form f of s is called a positive real function if it fulfills the four important conditions. That are, someone has switched off the mic, maybe please stop. Only when you speak, please switch on it. Fs should give real values for all values of s, and P of s should be a Hurwitz polynomial. And if we substitute s is equal to j omega, then on separating the real and imaginary part, the real part of the function should be greater than or equal to 0, means it should be non-negative. So this most important condition, this is the most important condition. We will frequently use this condition in order to find out whether the function is positive real or not. So on substituting s is equal to j omega, fs should possess full poles and the residues should be real and positive. These are the conditions for positive and positive real function. So properties of positive real functions, the numerator and denominator of fs should be, and the degree of the numerator of fs should not exceed the degree of the denominator by more than unity. That's what we have. Or m minus n should be less than or equal to 1 always. If f of s is positive real function, then reciprocal of fs is also a positive real function. So remember, the summation of two or more positive real functions is also a positive real function. So these are all the properties of positive real functions. Then comes the LC immittance function. So ZLC or YLC is the ratio of odd to even or even to odd polynomials, and then the immittance function has certain properties. So for example, half of real part, if this ZS is the impedance function of one port network, say, in that case, half of real part of Z into I square. This real part of Z means here the resistive component actually of R I square. This is the average power. It must be 0 in case of reactive network because only L and C components are there. In that case, the average power delivered to this network must be 0. So this is one condition. Similarly, another several properties are there for this immittance function. I'll go to summary directly. That will be helpful for you. Here on summary, the immittance function, the ZLC or YLC is the ratio of odd to even or even to odd in polynomials. The poles and zeros are simple and lie on j omega axis. When only L and C are involved, the poles and zeros must lie on the j omega axis because these the impedance of this inductance is j omega L and capacitance is 1 by j omega C. So both of them are imaginary. So you always expect poles and zeros are simple and they lie on the j omega axis, this axis. And the highest powers of the numerator and denominator must differ by unity. This is the essential condition. And the lowest powers also must differ by unity. So there must be either 0 or pole at the origin and infinity. So these are the basic properties of immittance function of LC circuits, and examples are here given here. So Z of S equals to K into S, for example, here you can see the poles in this case, zeros in this case are S equals to plus or minus 2J. So in this case, the poles are S equals to plus or minus J and plus or minus root 3J. So like this, all these functions are examples of LC circuits. And a synthesis of LC driving point immitances. So LC immittance is a positive real function with poles and zeros on the j omega axis only. And when you expand that into partial fractions like this, say for any given function, if you expand the z of s, say, in partial fractions, you have several components like this. So each of them has particular equivalent to particular network, elements. So the synthesis is accomplished by actually direct partial fractions, and Fs is impedance. Then the term K naught by S. K naught by S corresponds to what? Actually, you see 1 by Cs is capacitance, right? So therefore, here 1 by C corresponds to K naught, or K naught, or C corresponds to 1 by K naught farads. So here 1 by K naught farads. So like this term corresponds to a series capacitor. And K infinity, for example, this K infinity, so here infinity, you can see K infinity, this corresponds to inductance, because the impedance of an inductor in S domain is S into L. So this becomes, therefore K infinity becomes L. So like this, and this intermediate components also you can see, this corresponds to 1 by 2 Ki is the capacitance, and then this is the inductance. For example, LS, SL in parallel with 1 by CS. So if we compute this SL into 1 by CS, SC say, by SL plus 1 by SC. If we take LCM, then SL will remain, and then S square LC plus 1. So from here clearly, if you compare with this, with this, so 1 by 2K corresponds to L. Sorry, CC. If you divide this by 1 by L, S by 1 by L, sorry, L numerator and denominator, then S by C, LC you have to divide, sorry, S by C divided by S square plus 1 by LC, like this it will come. So when you compare, this corresponds to C corresponds to this value, and L corresponds to this value. So like this, way of synthesizing a network is called Foster-1 type. This is actually. So first we started with a series inductance and then series capacitance, and this is actually when Z infinity case. So last slide if we go, so this one, and the first term is corresponds to this capacitance. So then the intermediate terms, each terms corresponds to this 2Ki into S by S square plus omega I square. So which can be shown, for example, in this case 2 into S square plus 1, in this case into S square plus 9 by S into S square plus 4 can be expanded like this actually. So 2S is the 2 Henry here, and then 2 by S corresponds to 9 by 2 by S corresponds to this capacitance, and then this corresponds to the parallel combination of capacitor and inductor here. So this is Foster-1 form, and then this is Foster-2. In this case, instead of impedance, in the last network, we have done this for Z of S actually. So instead of impedance, we do it for Y of S. So similarly, we expand that into partial fractions, and then this kind of partial fractions are obtained. Then S here, and then this corresponds to the capacitance here, and then this term corresponds to the series combination of these two L and C, and this term corresponds to the series combination of these two. These basics you must have already gone through in your courses. And then another methodology is also available, that is Cauer form. So in this, this is a ladder network actually. So it is based on the continuous fraction method, expansion of the given impedance or admittance in continuous form. So the example I will explain you here how to expand that. For example, here Z of S is given. So Z of S equals to 2s to the power of 5 plus 12s cube, etc. This function you see here. So how to expand that? Now you see the denominator. Denominator s to the power of 4 plus 4s square plus 3. So by multiplying with what factor, the first term in the numerator will be eliminated. So just see that if you multiply by 2s in the denominator, this will become 2s to the power of 5 plus something it will become. So that's why if you do minus 2s from Z of s, the first term will go. So minus 2s into this, the denominator comes into picture. So when you take LCM, this becomes like this. So Z2s is obtained from Zs by using this. Or I can write Z of s minus 2s equals to Z2s. Or Z of s equals to 2s plus Z2s, Z2 of s I can write. And again this is Z2 of s. Now Y3 of s is actually inverse of, this is 1 by Z2 of s. You can see minus 1 by 4 into s. So Y3 of s is expanded like this. Now 1 by Z2 of s can be written as 1 by Z2 of s can be written as Y3 of s plus s by 4. Right. Now Z2 of s is simply inverse of this. Z2 of s equals to 1 by s by 4 plus Y3 of s. Now this becomes, Z of s becomes 2s plus 1 by s by 4 plus Y3 of s. Now if you expand Y3 of s again, you will again get a form known as Cauer form. Here it is given, of course. You can expand that and then see. So you will get, for example, for a network of like this, you will get like this. This plus 1 by this plus 1 by this plus 1 by this plus this. So like this, this network, this kind of network are called ladder networks actually. So any positive real function f of s or z of s can be expanded in Cauer form using this procedure whatever described here. And similarly in Cauer 2 form, Cauer 2 method, what is done is instead of impedance, we do it for admittance. So here we have done z of s. What will happen for z of s? Z2 of s we have written based on by looking at the denominator, multiplying by minus 2s, etc. But in case of Cauer 2 form, we have to do it for instead of impedance, we will do for admittance, y of s. So by then numerator becomes denominator, denominator becomes numerator, and using that we can expand into similar fashion, and then the Cauer 2 form also the network can be obtained. This you may use it as homework maybe. Now after this I would like to explain what is the use actually. Okay, these basics you will be learning in your BTech course also, or you might have already gone through. But what is the application? That's what important, because lab, whatever you learn in your class must be experimented with, or if that is not realizable in practice, then there is no use of such learning, right? So every part that you learn in your BTech, you must try to do it experimentally or try to understand what is the use. So can any one of you tell what is the use of network synthesis? Hello? Are you listening?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Application.
Sir.
Yeah. Someone said yes. Any simple application in practice, can you guess? Otherwise, can you tell if you know, or can you guess what is the use of this network synthesis? Okay, basically what it deals with, if you know a network function, you will you can if it is a positive real function and the denominator is a Hurwitz polynomial, and if it meets the conditions, then you can synthesize a network for that function, right? Network function, whatever network function is given. Then what is the use of it? In practice, what is the use? Where do we need it? Or if you have an example, then let me know. Here, first year students are there, second year or third year, all 3 years?
Sir, all 3 years, sir.
Okay. Then you must tell, where exactly, what is the use of this thing? Because you must see, one of the problems of Indian education is the focus is mainly on the theory. So this is the comment by one of the professors in US. They say that Indians are very strong in analysis, but when it comes to the lab, they are afraid to even enter into the lab. So such a comment was made by one of the US professors. So it is true also, because we study and we are very excellent in theoretical analysis, understanding or mathematical derivations, etc. But unless we make something realizable and understand something in practice, what is the application, then what is the use? So that's why I'm asking you, where do you think we can apply this one? Okay, then see, there are several ways this can be applied, even for designing a filter, or even for studying some phenomenon using a network. For example, some phenomenon is happening, and then there is a function available for that in terms of polynomials, say, or you may linearize to some extent to meet the real requirements to some extent, and then study that using a network. That is one thing. And I'll tell you one of the very important applications in power engineering. So in power engineering, you have gone through the transformers. Have you studied about transformer?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now transformer is one of the most expensive component in entire power network and power systems, and it has to be very, very carefully monitored for its health. And if a transformer fails, for example, it is not, I'm not talking about distribution transformer, I'm talking about power system transformer, which is power transformer. It's called a power transformer. It is very, very important, equipment in entire power systems, which has to be taken care of very carefully. Because failure of the transformer in power systems, power transformer is very, very expensive actually. The repair is very expensive, and then it also needs shutting down of that line and all. So in once in a 30 years, 40 years, if it fails, it's okay. But if it fails prior to that, then it is very, very expensive. Therefore, it is continuously monitored. Even offline or online techniques are also, of course, online techniques are not yet matured, but offline techniques are available. Now, without opening the transformer, because opening it means what? Opening it means you will be exposing the windings to the environment, and then that will have additional challenges. And there is oil in the transformer. This is insulating oil. Mineral insulating oil will also be used, and even biodegradable insulating oils are also being used nowadays actually. Not yet fully replaced, but they are going to come, biodegradable oils. Now in the transformer, we want to know the health of the transformer without opening the transformer. Okay. So by studying the the outside characteristics itself, means what are all the accessible things. Transformer basically has what actually inside?
Sir, coils.
Yeah, two windings will be there. I am drawing the two windings on different legs actually, but they may be concentric to avoid the leakage. Leakage means flux must link both windings equally. If it does not link both windings equally, then that is called, there is a leakage flux. So leakage flux has several other connotations and problems. So to avoid that, minimize that, both the primary and secondary windings are wound on a single central leg, one above the other. Primary will be inside and the secondary will be above that one, with adequate insulation between the windings. Now this is the transformer and the windings, and then this is kept in a tank actually, and from outside you will have access to, of course, access to these primary winding also. Of course, this can be ground. So here there is a bushing type construction you might have seen, that is porcelain construction, and then there is a circular electrode. The purpose of making this circular electrode is to avoid corona. Otherwise, a lot of corona will be there. And then say this is a low voltage winding, has a small bushing. There are two kinds of bushings. One is small bushing, one is big bushing. So small bushing is for low voltage winding, and big bushing is for high voltage winding. Like this, if it is a three-phase transformer, there will be three such things. Here, three such things, and then here also three such things. For each phase, you will have one. So this is the typical structure of a transformer. Now, whether internally the transformer is good or bad, its condition has worsened or not, or whether the windings are healthy or not, whether it has aged a little bit or not, is to be found. So in this case, what is done here is, So this is simply a network actually. Inside the transformer winding is there, no? But winding, what winding consists of? Winding has a simple wire which is wound on the leg of a core actually. This is a transformer core. And then it has what components? You see the winding has a resistance, and then there is inductance associated with this winding, because it is a winding. As long as there are turns, of course single wire also will have inductance, because there will be magnetic flux associated with even a single wire also. So if there are turns like this, then there is inductance associated with this, and there will also be capacitance between these turns, because each turn has a certain gap. The turns are separated by certain gap. Whenever two metal electrodes are separated by certain distance, and if there is a potential difference between them, then that will act as a capacitance. Therefore, there will be capacitances between the turns also, and inductances and capacitances, and then the wire also has resistance. Therefore, each winding is a ladder network like this. So a series resistance, I am drawing simply actually, it can be complicated further also. And then capacitance to, there is of course capacitance to the core also. See, each winding wire is separated from the core by some insulation. Therefore, core will act as an electrode which is normally at ground potential, and the winding is at high voltage potential. Therefore, there will be capacitance to core also from each winding turn. So this is parallel capacitance given here, and then resistance, and then inductance. And here, across the inductance, there is capacitance. Maybe you can interturn capacitance, you can assume this one. So this is a complicated ladder network. Each winding is a complicated ladder network. Now, since it is a ladder network, then what will happen if there is some damage in the winding? So what will happen to the, how it will reflect? Naturally, if there is a damage in the winding, then the corresponding capacitance or inductance parameter will change. So when the capacitance or inductance parameter will change, obviously the network function will change. So this is how by observing at the terminals. Now I am not opening the transformer. Please listen, I am not opening the transformer. What I will do is, I will conduct a test at this terminal using a voltage source, say V, and then like this. So it is actually a complicated one. I am explaining very simply in order so that you will understand and all. So here a voltage source I am connecting. This is offline test, not live. So a voltage source I am connecting from, the transformer tank is at ground potential, and one of the terminals is at high potential, and then I am finding out the current. Now I know the voltage, I know the current, I know the impedance function Z of S. This is input impedance function. Of course, there are several combinations of impedances here, transfer impedance, etc. I am simply saying V of S by I of S, I can find it out. Right? In frequency domain, I can analyze where zeros are there, where poles are there. And then from this, constructing a network, synthesizing a network can be done. So I'll keep this, synthesized network with all its parameters in the beginning of the beginning of installation of the transformer. Now I have this reference circuit of the transformer. Now over a period of time, in a regular intervals, I'll go and check the same characteristics from the terminals V by S, and then finding the frequency characteristics, which is known as Swift frequency response analysis, actually SFRA. Of course, that is I'm not talking about that now. using that you can synthesize a network. So each time I will compare my synthesized network with original network and see if there are any parameter changes. And if there are changes and at which portion there are changes, based on that I can even estimate the location of the damage inside the transformer, exactly where exactly there is a problem. For example, in transformer, what kind of damages you can expect? For example, under short circuit conditions, under such conditions, what kind of during faults, what kind of problems will be experienced in a transformer? Do you have any idea?
Turn to turn fault, sir.
Turn to turn fault. So why during the short circuit conditions actually heavy current flows in the line. Due to heavy current in the line, there will be force of attraction between the turns. So these turns tend to come closer and then ultimately damage the windings, damage the insulation between them, and then becomes short circuited, turn to turn short circuit. So in that case, there will be a difference in the network parameters that we estimate using the terminal measurements. So this is how a transformer health can be monitored. So it is a very, very useful tool which can be applied for a practical application where the condition of a transformer can be monitored, which is very, very expensive actually. So therefore this is one of the applications, and other applications include even filters, etc., and even communications. A lot of applications of this synthesis exist. Okay, so with this I will stop my presentation. If you have any further questions, please feel free to ask.